Let's look at some exercises from Lesson 1-1. Number 27. We have sets A, B, and the universal set. The universal set is natural numbers, so those are the numbers 1 through infinity. A has the elements 1, 3, 5, and 9, and B has the elements 2, 3, 7, and 9. You can see that I have already identified that A and B have the numbers 3 and 9 in common. Number 27 asks us to find each set, then draw and shade a Venn diagram. So number 27 is the set A in intersection with B, and then find its complement. So A in intersection with B and find its complement. Well, let's take a look. If A is 1, 3, 5, and 9, and B is 2, 3, 7, and 9, we know that we have the common numbers 3 and 9 in both. Let's do the first part of our set operation, and A in intersection with B would be the numbers 3 and 9. But that's really not what we were asked to find. We need that intersection, and then we need the complement of it. So the complement of this intersection will be everything that's not in that intersection. So that means that A in intersection with B complement would be the numbers 1, 2, 4, 5, 6, 7, 8, and 10. And everything in this box would be shaded with the exception of the 3 and the 9. Let's look at number 29. 29 says A in union with B in intersection with B complement. So let's first find out what A in union with B is. So A in union with B would be 1, 2, 3, 5, 7, and 9. B complement would be everything that's not in B, which would be 1, 4, 5, 6, 8, 10. Now let's see if we have anything in common between these sets, and we do. We have the numbers 1, and we have the numbers 5. So let's start again. A in union with B in intersection with B complement was the numbers 1 and 5. Number 35 is a little more complicated. We have 3 sets, M, which is 0, 2, 3, and 6, K, which is 0, 1, 2, and 5, and then the universal set, which is X is greater than 0 and X is greater than or equal to 0, or X is greater than or equal to 10. So it tells us in 35 that we're to find the set M. So in number 35, we're to find M in intersection with K, complement, in union with M complement in intersection with K. And this is not supposed to be there. So let's first take a look at our sets. We know that M, our first set here, was 0, 2, 3, and 6. Now we're looking for a K complement. That will be everything that is not in M, but is also in the universal set. So K complement is 3, 4, 6, 7, 8, 9, and so forth. We're looking for intersection. So is there anything in intersection here? Absolutely. We have the numbers 3 and 6 that are in intersection. So M in intersection with K complement is the numbers 3 and 6. Now let's go to our second operation. We need M complement. So M complement is everything that is not in M. So M complement would be 1, 4, 5, 7, and 8. And set K is 0, 1, 2, and 5. Is there anything that is common between both of these? Yes, we have the numbers 1 and the numbers 5. So M complement in intersection with K is the numbers 1 and 5. Now we're going to do our set operation and add these together because it's asking for union. And we have the numbers as an answer, 1, 3, 5, and 6. Let's go ahead and fill in our Venn diagram. We have set M and we have set K. And what do M and K have in common? Well, they have 0 and they have 2. What's left in M would be 3 and 6. What's left in K would be 1 and 5. And these are the answers that you saw right there. So this would be shaded in M. This would be shaded in K. The overlap would be left unshaded. Number 46. The instructions are determine whether each statement is always, sometimes, or never true. If sometimes, explain when. So, in number 46, it says A in union with B equals A in intersection with B. Would this be always true, sometimes, or never true? Well, let's do a couple of examples. If A were the elements 1, 2, and 3, and B were the elements 4, 5, 6, would they be equal? No. They would never be equal because they are different elements. Now, they are equivalent because they have the same amount of elements. But is that the end of the story? Could we make this a true statement? Yes, we could. If A had the elements 1, 2, 3, and set B has the elements 1, 2, 3, they are now equal, and they would always be equal. So the answer here would be sometimes when the sets are equal. Okay. And the last one we're going to do is number 50. For 50, we need to show that the even positive numbers are countable. Those numbers would be numbers like 2, 4, 6, 8, and 10. This is a great answer, but a better answer would show that they're always countable. And there's a pattern there. The pattern is 2 times a number is countable. So 2 times 2 is 4. 4 is 2 times 2. 6 is 3 times 2. 8 is 4 times 2. 10 is 5 times 2. And this is how you would express that. And this is a pattern, and one of the ways you could write this down would be to say times 2. So 2 times 2 would be 4. 3 times 2 would be 6. 4 times 2 would be 8, and so forth. Hope that helps.